Greetings. The problem 5182 from the book Thermodynamics by Senja is an interesting problem because the problem looks pretty straightforward, and reaching the answer as the book has required is pretty simple. But there are very intricate points in the problem which I shall discuss them after I have solved the problem and reached the answers that you just see on the picture. Now, let's see what the problem says. The problem says that there is a piston cylinder device, and as usual, I try to, in fact, interpret the problem into a thermodynamic language. And that's very important that you should always be doing. So the problem tells us that there is a piston cylinder device, which perhaps would look like this. And it initially contains, so we have initial condition and we have final condition, and we have to take care of both. Initially, so initial condition, initial condition. The initial condition is that M1 equals 2 kilograms. And what does it have in it? It has R134A. So it is R134A. This is um, what is inside this cylinder piston device. And it initially contains 2 kilograms of R134A at 800 kilopascal. P1 equals 800 kilopascal, and T1 initial temperature equals 80 degrees C. It tells us that at this state, the piston is touching on a pair of stops at the top. So there are a pair of stops at the top. Assume that there are a pair of stops at the top, and the piston can't go any higher. So if it is pushing, it means that the pressure 800 kilopascals inside the cylinder piston device is more than just required for piston floating over the R134A, and R134A has higher pressure than piston weight and the atmosphere would produce, and therefore is pushing at the top with this pressure. The mass of piston is such that a 500 kilopascal pressure is required to move it. So if the pressure is reduced to 500 kilopascals, then the piston would start moving down. So the pressure at the top, this pressure is P equals 500 kilopascal, and the pressure underneath is 800 kilopascal to begin with. But let's see what happens next. It says a valve at the bottom of the cylinder is opened and R134A is withdrawn from the cylinder. So there's a valve underneath. There's a valve underneath. The valve is open and R134A is let out. Now, so what we expect is that we expect that the pressure would reduce and it would eventually reach 500 kilopascal. And by that time, there would be an equilibrium pressure between the pressure inside R134A and outside. I mean, this line would have equilibrium pressure after After a while, when the pressure inside is 500 kilopascal, and if we let more R134A out, then the piston would move down. Now, it says after a while, which is the time when the pressure inside is between 800 kilopascal and 500 kilopascal, the piston is observed to move. So the piston would start moving. So there are initial condition one. There is the intermediate condition, let's call it intermediate, and what that is when V2 equals V1, P2 equals 500 kilopascal, okay, P2 equals 500 kilopascal, and uh, the piston, just after this time, the piston will start moving down. So after a while, which is between condition 1 and condition 2, and the pressure is dropping between 800 and 500, it says after a while, the piston is observed to move and the valve piston is observed to move. Okay, so this is, and the valve is closed, but half of the refrigerant is withdrawn from the cylinder. So at the final condition, and let's call this final, what happens? P3 equals P2 equals 500 kilopascal because however mass we let out of the valve, the piston would move down and keep the pressure at 500 kilopascal. So the pressure would remain constant between points 2 and 3. And it says that uh, at point 3, M3 equals half M1. So easy to calculate, but still, it says that the valve is closed when half of the refrigerant is withdrawn from the cylinder and the temperature in the tank drops to 20 degrees C. So T3 equals 20 degrees C. And now what it asks from us is that calculate work done. So there are two requirements. W, the work done, and then the heat transfer. So Q. This is what the problem has asked from us. The problem asks nothing about point 2. Now, if we solve the problem and reach the answers that you see, that would be very easy. And what we shall do is to solve the problem between points 1 and 3. Now, if we wish to consider point 2, then you will learn quite a lot of information and you would see how different our answers would be when we understand how point 2 behaves or could behave. And therefore, these answers could easily change if you consider point 2. But a simple look at the tables for R134 would tell us that T critical is 374.2 Kelvin, which is very, very close to the range we have. So between 20 and 80 degrees C, it would be 293.15, and this would be 353 kelvins, 353. This is just a critical point is just above this point, or our points, our process happens just below the critical point. But the P critical, the critical pressure is 4.059 megapascal, and therefore looking at 800 kilopascal and 500 kilopascal and comparing with this value, the temperature is almost about the same as the critical point. The pressure is 5 less. It's about 1/8 of the um, critical point, and therefore we could well assume that we are in superheat condition for R134A. And let's have a look at it in the table to see what that tells us. Well, the table tells us that at P equals zero point 0.8 megapascal, which is 800 kilopascal. The saturation temperature is 31 degrees C, 31.31, and so at 80 degrees C, we are well in the superheat region, and for 80 degrees C, we have quite a number of properties which we could write down. So V1 would equal 0.032659, and U1 would equal 290 per 84, 290 per 84. This is kilojoule per kilogram, and that is cubic meters per kilogram. And H1 equals 316.97, 316.97 kilojoule per kilogram. Okay, we're solving this problem within the limits of the first law, so we won't need any information on entropy. Just above this uh, place in the table where we just read properties for point 1, we have our point for point 3. And at 20 degrees C, which is the temperature for 500 kilopascal, we would have these information. It tells us that at 500 kilopascal and 20 degrees C, there's still superheat, and the properties are as follows. V3 equals 0.042115 cubic meters per kilogram, and U3 equals 242.40 kilojoule per kilogram, and H3 equals 263.46 kilojoule per kilogram. So basically, we have all the required knowledge for points 1 and 3. And we know the initial condition, we know the final condition, and about the process, we vaguely know what happens because we know that you open the valve, there could be heat transfer, they certainly work after the piston has started moving, but how their combination works, we don't know. So, but as we know the properties, we could easily go to equations and see how do they simplify. Now, we have all properties for initial and final condition. Let's simplify the governing equations to see how they would look like for this problem. You see, what I would do is first, and that's important, to select the boundary you want to study. And the boundary you want to study, the control volume, is the R134A, so long as it stays inside our cylinder piston device. I mean, if it leaves our boundary, if it leaves our cylinder, then it won't be inside our boundary. So we have a control volume inside our cylinder piston, and we want to simplify the governing equations for this very boundary. Well, here are our governing equations, and our problem has initial and final conditions. So this term would be integrated to M3 minus M1, and this one would be M3U3 minus M1U1. There is no change in velocity, and there is no change in elevation. So velocity change and elevation change would vanish from equations. Um, there is no mass going into our cylinder piston device. So this term m dot I and this term, the energy within going and mass would vanish, but this term is there. And this term also, these two terms are also present. Now, simplifying the first equation, the mass conservation equation would tell us that M3 minus M1 equals no mass enters, but mass leaves. So it is ME, and we are integrating this equation between initial and final conditions. And for the energy equation, it is M3 U3 minus M1 U1, which is the difference between initial and final energies, would equal no mass enters, but it is the mass that leaves, ME. HE, and between 1 and 3, both heat transfer and work are present. Of course, heat transfer is present throughout 1 to 3. Work is only present between 2 and 3 while the piston moves, but as it is, we uh, we have to take it into account once we are integrating everything between 1 and 3. Well, in this equation, uh, properties of points 3 and 1 are known. We have everything. Here we have masses and energies. The mass that is leaving the control volume could easily be calculated. Initially, there is a 2 kilogram, and half of it leaves, so 1 kilogram is left, and 1 kilogram remains in the cylinder. HE, we should assume to be the average between H1 and H3, so the average value should be taken. Q we don't know, and W is easy to calculate since it's a constant pressure process, and we only need the integral P dV, and constant P, it makes it P times V3 minus V1. So the only unknown in this equation perhaps is Q, and we shall calculate it right now. So W equals P, the pressure, and when the piston starts moving down, this is a constant pressure process, P times V3 minus V1, and that equals P times M3 V3 minus M1 V1, uh, and that equals 500 kilopascal times M3, which is 1 kilogram, times V3. We know the value. It is 0.042115, and minus M1, which is 2 kilogram, times V1, which is 0.032659, and the outcome for W would be um, minus 11.6 kilojoule. Please note that W is a minus, and minus sign should be there, since work is done on R134A. I mean, the environment is doing work on R134A, and the piston is moving down. So the work should be negative, and that's the sign we have here. Also, a very simple other point that we have to calculate before we start calculating. This one is that HE equals H1 plus H3 divided by 2, and that would be 316.97 plus H3, which is 263.46, and divided by 2, and therefore HE would be 290.2 kilojoule per kilogram. Now, you see we have everything we require for solving this equation and calculating Q. Finally, putting numbers to this equation would be M3, which is 1 kilogram, which is 1, times U3, which is 242.4, and minus M1, which was 2 kilograms, and U1, which was 290.84, and that equals ME, the mass that has left the control volume, minus 1, times HE, which is the average enthalpy, and that is 290.2, plus Q, and minus W, which is minus 11.6. And the outcome for Q would be minus 60.7 kilojoules. This is also a negative value, since this since heat is leaving our control volume. Well, these are the two answers that the original problem had asked from us, that the calculation was pretty simple and straightforward. There looked no problems, but there's a very important problem which shows itself if we try to calculate where point 2 could be. I mean, there is a point 2 in between, which we haven't looked at it. And if we look at it where the point 2 is, then we would learn very interesting points that would basically change our calculation for Q and give us very different values And that's what I shall do in the next video. Thanks for watching and see you in the next video.